All right, so today we're going to be continuing our conversation on on transformers. We're going to be talking a bit about grounding and bonding of transformers, as well as touching on sizing of overcurrent protection for transformers. So we're going to start with an introduction to the National Electrical Code. Anyone who's in the electrical industry doing electrical installations inside buildings should have a copy of the National Electrical Code. As it's not an installation manual at all, but it does provide the codes, the rules, if you will, for installations of various systems. For transformers, that is covered under Article 450. The National Electrical Code is broken into multiple articles, and it's covered under Article 450 of the National Electrical Code. It covers things such as overcurrent protection, guarding, ventilation, grounding, terminal wiring space, and disconnecting means, all covered in these sections, but also reference other areas of the code. So like grounding is actually covered under Article 250. So while, or that says guarding. 450.10 grounding, well, that will actually reference Article 250. And so the National Electrical Code is sort of set up that way to where you're jumping around the code a lot, and it's kind of one of the things that makes it a little bit challenging to learn, because you might be looking in this area of the code and it references you to somewhere else in the code, and you have to keep in mind your context as you're moving around that book. NEC articles on grounding and bonding are covered. So we have Article 250, as I mentioned, covers grounding and bonding, and it's broken into multiple parts. Article 240 covers overcurrent protection, and as mentioned already, 450 covers transformers. So this isn't really a code class, just wanted to give you guys some reference that this is where we're going to be pulling some of the rules from, is from the National Electrical Code. So we'll talk briefly about locations, installation locations. Outdoor units are typically the same in terms of how they operate. They're the same, right? The coils, the way they work in theory and all that, none of that changes. It's really just the construction. Just like anything that we install, if you install something indoors or outdoors in hazardous locations, you just need to make sure that what we're installing is rated for the area. And dry type transformers typically can be converted, like a lot of the ones we install can be converted to NEMA 3R simply by ordering a rain shield and installing that on the transformer, whereas some are just come as a fully enclosed weatherproof enclosure. So this is just to say, pay attention to the ratings of what we're installing so that it matches the environment. We are allowed to actually install some transformers above acoustical ceilings or non-structural ceilings. The National Electrical Code defines suspended ceilings as a dropped, suspended, or similar ceiling that does not add strength to the building structure. Therefore, it shall not be considered a structural ceiling. And so we don't really do a whole lot of these, but I have done a handful in my career where we do hang a transformer above a suspended ceiling. And so long as the ventilation is okay, so like if there were insulation up there, you couldn't like sit it in the insulation. You would still have to observe all the required ventilation and clearance requirements for that transformer. But transformers are not required in many instances to be readily accessible. They're only required to be accessible. That's a code distinction that we can get into in a future class, but just basically means you can reach it with a ladder. Tools are allowed to be used to get to it. It doesn't have to be readily accessible. Yeah, we're all very familiar with acoustical ceilings, so don't really need to talk too much about what they are. We know what they are, but there are limitations to when we can put them above a suspended ceiling, and that would be 50 kVA and less, or operating at 1,000 volts or less. And so we almost never see anything up 1,000 volts. In fact, I've been 26 years. I've never touched anything over 480. So that's pretty rare for the types of commercial buildings that we do. But yeah, 50 kVA rating of a transformer and less, you can install it above a suspended ceiling. clearance requirements. So most transformers, if you are going to be fully enclosed, and so there's some information on this slide, I believe, that has more to do with like if you had open coils. Actually, we have a picture of one with an open coil that we'll see, but most of the transformers that we actually install um, are going to be fully enclosed. So they're gonna have a full metal enclosure, and so some of this isn't going to be something we see that often. But if it weren't constructed as such, then we'd have to maintain at least 12 inches from combustible materials, unless separated by a fire-resistant, heat-insulated barrier. Like I said, we're installing transformers that are in an enclosure, and so that being the case, we need to follow the manufacturer's recommendations on that. And so you can look up the product, or maybe it's listed on the transformer. I've installed zero clearance transformers, so you could slap these things right up against a wall. Probably has to be a non-combustible wall, but or sometimes I've done them where the clearance is only 2 inches. So it's either follow the manufacturer's UL listed requirements. Absent of those, our clearance has to be 12 inches from combustible material. We also need to observe working clearance. So even if you install a transformer above a drop ceiling, you still need to follow working clearance rules. So Article 110 of the National Electrical Code, 110.26, is where we can find information regarding clearances around electrical equipment. Typically, so if we're doing like 120, 208 volt systems, our clearance in front of equipment needs to be 3 feet. Once you get above that, it's going to be 3.5 feet. And there are some nuances to that, to where that that clearance requirement increases, but those are sort of the minimums. And we'll probably get into some actual detail about working clearance in a future class, because that can be like a whole discussion. Okay, so grounding and bonding. This is the part that I really wanted to make sure that we drive home, is understanding why we ground, why do we install equipment grounding conductors, what is a grounding electroconductor, what is bonding, and why is it so important? So we need to remember 2 things, right? Electrons move in a closed circuit. Right? They move from the source and back to the source. A lot of times when we ask somebody, well, where are electrons trying to get to? The answer at first, folks will say, well, it needs to get back to ground. It needs to get to Earth. This is why we ground circuits, so that electrons can get back to Earth. That's not the case, unless you're talking about lightning, in which case the source is the Earth, right? And so electrons move in a closed circuit. We learned this last week with the transformers, where the electromagnetic field induces an electromotive force into another conductor, and electrons in that conductor will flow if it is a closed circuit. So a circle, right? A closed circuit, and usually, if it's wired correctly, would be closed, going through resistances, through loads, right? So electrons are moving in a closed circuit from the source back to the source. That's an important thing to remember. And then the other important thing to remember is that the only way to make a system safe is to remove the voltage. You can put, we're not, this isn't a PPE class, but some might say, well, no, I can make it safe by wearing PPE. No, that's working safely, but to make the system safe, you have to remove voltage. Okay, so remember those 2 things as we talk more about this. And so in the case of lightning, right, we can see where you can see this. There's the circuit flowing here from the upper atmosphere to the ground, right? And so this circuit is being completed through the atmosphere back to Earth, right? So the source here is the planet, right, with lightning. And so if we have an indirect lightning strike, that's a massive amount of energy. It's going to that's going to have its own like EMF, if you will. that will excite electrons in metal parts of structures. And so those electrons need to get back to the source, needs to get back to Earth safely. And so this is where grounding comes into play, is so that we can get this energy, lightning energy, and really indirect lightning energy is what we're concerned with. Because if you take a direct lightning strike, it's pretty much over. We're not really trying to protect against that, a direct lightning strike. But indirect lightning strikes, we need to get that energy back to the source safely. If we don't, then what happens is you end up having arcing across loose metal parts of steel in a building. It could arc across, and of course that creates a fire hazard. Indirect lightning strikes will induce additional energy into our actual wiring on our systems too. And so by grounding our systems, we provide a way for that energy to get back out of our systems without arcing across electrical parts or degrading electrical insulation. Because if the voltages get very high, the insulators can actually start to become conductors if it becomes high enough. And so insulation will also break down. And so this is where, where grounding was introduced in the past, is prior to grounding happening, insulation would fail more frequently, parts would fail more frequently. And it was a result of this indirect energy from indirect lightning strikes either being introduced on the utility, right? It could get into our buildings by being introduced into the utility lines, and then, to our meters. And then, so this is why it's good practice to install this grounding electroconductor system as close as possible to the point of service. And now actually code requires us to install that grounding electroconductor at the main service disconnect. And there's a good reason for that. So we can get that energy from the utility, this lightning energy from the utility that might come in on the utility lines, out of our systems as quickly as possible. Right. Kind of talked about that longer than I should have probably. Meant to change this picture, but for transformers with no direct connection to the primary, so these are the kinds of transformers we talked about last week. We have a primary coil and a secondary coil, and they don't have any electrical interconnection. They're only linked through induction. In that case, the source is the secondary winding of our on-site transformer. We call that a separately derived system, by the way. And so in that case, the power source is our transformer. Okay, so that brings us to system bonding. So bonding is the connection that ties our grounding electrodes, grounding neutral, and grounding conductors together. Grounding electrodes, grounding equipment. I think I meant to say equipment grounding conductors together. And by bonding them together, we establish a low impedance path for fault current to flow back to the source. Low impedance just means low resistance. So by bonding those all together, so bonding just means to connect all these parts all together. This bonds them all together. And so if we see in this illustration, well, let me finish actually reading the slide here. The low impedance resistance allows for high currents, the magnitude of which can open an overcurrent device. So let me remember what I said. We want to remember two things: that electrons move in a closed circuit from the source and back to the source. And also the only way to make a system safe is to remove the voltage. Right. So we have a photo here. This is actually from one of our air curtains. The inside of the enclosure has this control transformer in it. And we can see that there is a connection made from this secondary terminal to ground, right? And so we could call this a system bonding jumper, right? This is connecting this metal plate, which is connected to our equipment grounding conductors. So this metal plate is grounded and is connecting to one side of this transformer, which is tied to, I believe this is 120. Yeah, this is 120 volt secondary on this transformer. And so what this will do is, if the other side of this circuit, this L1 side, this black conductor, if there's a fault on this circuit, what that will do is that when this wire touches ground, is it will complete the circuit back to the source, right? So if we disconnected this green wire and we touched this other side to ground, electrons will not be able to flow back to the source, right? Because we haven't closed the circuit. And so by doing that, by grounding in this way, by bonding in this way, we close the circuit. And since it's a direct short, we are going to introduce a very high amount of current up to the limits of this transformer will be introduced into the circuit, right? So that will introduce a high amount of current, high enough to trip a circuit breaker or blow a fuse, right? So if this conductor was not here, then and we had a short circuit, the overcurrent device would not open. This is very important to remember. This is a critically important connection here, this little green wire. And it's something we have to think about whenever we're installing an electrical service. So if we have power coming in from the utility company, that is an ungrounded system until we ground it at our service disconnect switch, or bond it at our service disconnect switch. So that what I mean by that is it's connecting that neutral conductor to our grounding electro conductor to our equipment grounding conductors to tie that all together, right? So we have to close that circuit. Otherwise, we will not be able to open overcurrent devices, and we will have serious electrocution hazards present in our buildings. So if you are installing transformers of any size, anything over like maybe a little 50 VA transformer, you need to start thinking about bonding. And if you don't have a firm grasp on this, I'd like you to try to set up a meeting with me, and we could spend more time just really nailing this, getting this nailed home to understand these concepts. But just always be thinking about this when you're installing transformers. Am I bonded? How do I bond? We want to make sure that this happens with every transformer we install. There are ungrounded systems out there. Not going to talk about them. I haven't installed a single one in 26 years. So as far as I'm concerned, it's fake news. They're out there and they have purpose, but we don't typically do them. This is a slide that I put, something I put together many, many years ago, just to sort of illustrate some grounding and bonding scenarios. So we have, it's probably too hard to see. So I'm going to just go over this quickly, but I shared this material with you guys this morning so you could take a closer look at this. This basically just shows a distribution system where we have a utility transformer with conductors that do not bring in an equipment grounding conductor or grounding electroconductor from the utility transformer to our meter. And then we have a service disconnect switch. And at that service disconnect switch, we are bonding our system. We have our grounding electrodes, we have equipment grounding conductors, and our neutral are all landing on this system bond bar in our main service disconnect. And if we're no separately derived systems on premises, this would be the only place that we would bond. But in this illustration, I am showing a yellow square that represents a separately derived system, in this case being a transformer. When we have a separately derived system, which just means that your primary and secondary coils do not have a direct connection. They're only linked through induction. Generators can also be separately derived systems, but we're going to talk about that in another class. Then we have another bonding point here, which is connected to the XO or neutral terminal of our secondary in our transformer. And so we're also going to bond here so that we can complete that circuit, have that closed circuit, that low impedance path to ground on our secondary system as well. So this is an illustration with two systems. You have the system from the utility, and then you have a separately derived system. There's plenty more to talk about that, but we have a lot of slides to go through, so I'm going to continue moving. So electrodes permitted for grounding. There are several. Metal underground water pipe, not so common nowadays, but back in the old days, metal underground water pipe was very common. And so it would be actually very important that you bond those. And in the case of bonding, if you did have incoming metal water pipe, there's something very important to remember. which we don't really see this in Florida. I saw this more back in Massachusetts. But we would have to make sure that you jumped the meter. Probably not worth really getting into that, but if you take the meter out, you lose your grounding electrode. So how you connected that was really important. Metal in-ground support structure. So this just means structural steel. It says direct contact with ground must be greater than 10 feet. So, if you have a structure that's a steel building, you still have to bond it. But so you're always going to have a connection to steel, but whether or not that steel qualifies as a grounding electrode is the important distinction here. Most of the time, the structures that we see don't have a metal in-ground support structure that has 10 feet in contact with the earth. Those bolts that they use to install them, I don't think they're 10 feet long, but we are always going to have to bond them. So that's something important to remember is, okay, is that structural steel a grounding electrode or isn't it? Does it really matter to us? No, because we're going to connect to it anyway. Concrete encased electrodes, there's two ways to do this. To hook up to a concrete encased electrode, either, and I usually am just redundant because I don't know what the inspector is going to want to see. Actually just went and did one Monday, where I'll put 20 feet of copper in the footer, and I will also install a ground clamp on a piece of rebar that's at least 20 feet long. So I'm kind of being redundant there because I don't know, my inspector might show up and be like, I want to see it this way. So I just do both, and they're always happy. So concrete encased electrode. So the footer has to be in direct contact with the ground. So that means if there's visqueen underneath the footer, it doesn't count. It's not in direct contact with the earth. And so in that case, we would have to install maybe a separate concrete encased electrode, something like that. These are, so the ones that are required here are metal underground water pipe if present, concrete encased electrodes if present, metal in-ground support structure if present, required. Ground ring, optional. Rod and pipe electrodes, these are also called supplementary. I'd have to confirm whether or not what I'm about to say is correct, but my understanding was always that these are simply supplementary electrodes with, we always install them. So I don't want to dig into that and give you guys any misinformation. We always install them, and you just space them 6 feet apart. I'd have to look up the ifs and thens as to when you do and don't, when you are and are not required to have those. There are several that we have access to in any given structure. This is the same slide. Okay, AC systems to be grounded. All AC or alternating current systems of less than 50 volts to ground must be grounded under any of the following conditions. So if the transformer supply system exceeds 150 volts to ground, if the transformer supply system is ungrounded, and if installed outside its overhead conductors. I don't really understand that third one, but that is in the code. Install a transformer outside its overhead conductors. I don't understand that last line so well, but if your transformer, so when do we have these? So we do actually see a lot of these that are less than 50 volts, probably in our HVAC systems. Those are, of course, those are usually class 2 transformers, where the transformer supply system exceeds 150 volts to ground. Yeah, we're going to see that a lot. You might have a 240 volt supply, and then your secondary, I guess your secondary in your HVAC systems is usually 24 volts. And so maybe we're not going to see a secondary grounded that frequently, actually, in AC systems of less than 50 volts ground. Oh, so this is inclusive of 24 volts. Interesting. So there's probably a lot of bonding out there of our secondaries to ground that is not happening. So this is something we want to make sure that have a full understanding of. So that would be one situation. AC systems of 50 volts or less to ground must be grounded in any of those circumstances. What we're going to see more frequently is this type B. AC systems of 50 to 1000 volts must be grounded under any of the following conditions. So the system can be grounded so that the maximum voltage doesn't exceed 150 volts. If the system is three-phase, four-wire Y connected and has a neutral as a circuit conductor. If the system is three-phase, four-wire delta connected and uses the midpoint of one winding as a circuit conductor. So this is essentially like if you're using a system, you have neutrals basically in your system. Is we're saying it must be grounded. Believe it or not, there are scenarios where you don't have to ground transformers, but like I said, I have not experienced those. And so in this illustration, this is like what we talked about a little bit earlier, where this is a transformer that has 480 volts on the primary. So that meets one of these conditions where it must be grounded. The supply system exceeds 150 volts to ground. So 480 volts incoming. That means we have 277 volts to ground. So this is one that must be grounded. This is non-optional. So it's good to see that they've done it. Grounding electroconductors. What did I have this slide for? So I just wanted to show that this is something that we do frequently in new construction, where we interconnect all of our grounding electrodes by a ground bar inside of our main electrical rooms. So this one here, we have our footer steel. One of these conductors coming in is our footer steel. Another one is our ground rods. And then some of these other conductors are going off and feeding a transformer and various other areas. So we have our grounding electrode conductors coming in from our actual grounding electrode conductors. And then we have our grounding electrode conductors that will extend from here to our various sources. In this case, there was we had two service disconnects or something to that effect, and a transformer on this building. And so that's why we have all these conductors on this bar. Main bonding jumper connects the grounding circuit conductor and the equipment grounding. So there's just, there are, when you're reading through the National Electrical Code, you've got grounded conductors, grounding conductors, main bonding jumpers, system bonding jumpers. There's all these different names for these conductors that we never use really out in the field, but are relevant when you're reading through your code book, because context matters. And so your main bonding jumper and your grounding electrode conductor have different sizing rules. And so you just need to know what you're working with in order to effectively use the National Electrical Code to size your conductors properly. If you're studying for your license, this is stuff you want to learn. If you're an installer, you're not really looking to get your license, this is going to be like some nuanced information that you're not going to need on a day-to-day basis. So, I'd say I'm not going to spend a whole lot of time on that. Materials, materials must be made of copper, aluminum, copper-clad aluminum, or other corrosion-resistant materials. These are all the materials we would normally use. It's aluminum can't be installed in direct contact with earth. So for your grounding electroconductor that goes out to your ground rods or your footer steel, that has to be copper. Can't use aluminum for that. It will corrode very quickly. Ground screws, they have to be green. Believe it or not. This is a rule. Well, there's some good reasons for this, for the construction rules with ground screws, by the way. You'll notice that the thread count on a ground screw is 32. So 1032, I believe what that means is 32 threads per inch. Correct me if I'm wrong. But if you take the thickness of our box, which is, I don't know, maybe a 1/16 of an inch tops, we're required to have at least 2 threads engaged with the metal of something that we're grounding. You need at least 2 threads. And so 1032 ground screws, that thread count for the thickness of our boxes will engage 2 threads. So that's why they're 1032 screws. They do make self-tapping screws that are green and have the appropriate thread count that you can use for grounding boxes. I've been in this situation before myself where I've got to ground this box. I don't have any 1032 screws. I've got these tech screws. And so I take it out of my bag and I screw the box. Honestly, I'm not saying to do this, but if the alternative is I'm not going to ground this box, then use a tech screw. But the right way to do this is going to be with 1032 screws. And if you're going to make heavy use of self-tapping screws, then get ground-rated self-tapping screws. We should have run across this too much, and I'm not encouraging you to do this. I'm just saying, don't ever not ground something simply because you don't have a 1032 screw if you do have something else. But then just make sure that you get the right thing in place. Like, I don't want energized equipment out there without grounding enclosure. So something is better than nothing. Or maybe just don't turn it on until you get the ground screw. Giving all kinds of mixed advice here. Okay, 1031. Let's see. This illustration just shows where we are grounding on a Y-connected system. We have our neutral comes off of our XO terminal. This is a transformer that's in progress right now. You can see the grounds haven't been landed yet, but there's this XO terminal is where this white wire, terminal terminates. This is our XO terminal. And you can see there are extra termination points here on the bottom here. And this is where our grounding electroconductors and our equipment grounding conductors, system bonding jumpers, all those various types of grounding conductors will terminate on this bar. And we can see it's interconnected by this plate here. Right. So this is a three-phase transformer, Y connected. We can't see in the photo, but one side of these transformers is terminating to each of these lugs. And then our XO terminal has the center point of each of these coils behind it connected to it. And then that's our neutral, and we're also grounding that point in order to close the circuit so that we can get fault current back to the source, pull more current and pull enough current to trip an overcurrent device. And so this is just the diagrammatic representation of that to show where your ground connection terminates. It's at that center point here. And this is for a Y connected system. Sizing of ground electroconductors. So 256.66 in the National Electrical Code covers sizing of grounding electrode conductors. And so we have a table here set up that shows the size of the largest ungrounded conductors or equivalent area for parallel conductors on the left here. So if you have copper conductors for your line sets, your line 1, line 2, and so on conductors, if it's number 1 or 1/0, you're going to have your grounding electroconductor is required to be 6 gauge if copper or 4 gauge if aluminum. And then if they were parallel conductors, what you would do is you would just take the equivalent size if you have parallel. So let's say we had aluminum conductors that were parallel 250s. All right. So the equivalent of parallel 250s, 2 sets is 500s. So then we would be in this section here of over 250 through 500. Or that's a bad example because this keeps us in the same category. Let's say we had 3 parallels, then that would make the equivalent of 3 250s would be 750. And so that would push us into this category here of over 500 through 900. This would be the sum value of our parallel conductors. Then we would have our copper grounding electrode at 1/0, or aluminum would be 3/0. We will see engineers put 3/0 grounding electroconductors on every transformer, regardless of the size. If it's on the drawings that way, I guess we kind of have to do it. But this is where you can go to size that. So 250.66 is for grounding electroconductors. And then here's where I was talking about where understanding what your conductor is. So you're looking at the right code, because we have 250.102, which handles our grounded conductor. Grounded conductor being our neutral conductor, main bonding jumper, system bonding jumper, and supply side bonding jumper for alternating current systems. We could see that. So if we had that same scenario where we had 750 gauge, we were looking at 1/0 copper or 3/0 copper for this table. It's the same. Where is the difference? This is where code can get like, come on, guys. You're making this more complicated with multiple tables. So it is what it is. There's 2 tables. In this scenario, there's probably a nuance in here somewhere, but I can't see it. This is actually an article I don't visit very frequently. Yep. So that's those. And then, for ground, where you're going to see some bigger differences in your required sizes is in your equipment grounding conductors, which I don't remember that article. I think it's 250.122 for equipment grounding conductors. And that's what you guys have the most experience with, is with equipment grounding conductors. That's that green wire that we pull with every branch circuit, every feeder that we install. That ground wire is called an equipment grounding conductor. And so that's not sized in either of these tables that we're discussing. That is sized based on overcurrent devices, not the size of the line conductors. That's the distinction with your equipment grounding conductors. So overcurrent protective devices. Okay, so this is the part where we started out talking about the two things we needed to remember. One is that electrons only flow in a closed circuit, and that they are trying to get back to the source. And so that's why we do all that bonding of our neutrals to our equipment grounds and such, so that we can get electrons back to the source. Okay, once they get back to the source, we need an overcurrent device to open, right? That's the second part, where the only way to make a system safe is to remove the voltage. And so if we've done our bonding, we've sized our bonding conductors and our grounding conductors properly, everything is connected to the proper torque ratings, everything's connected up nice and solid, and we've established a low resistance path back to the source. What's going to happen is, if then when we have fault currents, fault current being line 1, line 2, line 3, making contact with ground, with what we call non-current carrying metals, right? They carry current because they're metal, but when we say non-current carrying, we mean they're not supposed to carry current. We want to remove that voltage. That's why we grounded it. So when we do that, when we complete that circuit, we're going to have a very high amount of current. And the reason we're going to have a very high amount of current is because the only resistor in the circuit is our grounding conductors, our equipment grounding conductors. That's the only resistor in the circuit. And because they're all great resistors, that resistance is very low, which means current is going to be very high. And overcurrent devices are designed to open under those circumstances. And so great. So we've grounded everything. We have primary overcurrent protection and secondary overcurrent protection. We should expect these devices to open, so long as it's all been wired up correctly. Of course, we know overcurrent protection can be something that could be a circuit breaker or a fuse. Either is fine for protecting transformers. We have some rules, or some rules here for how to go about sizing our overcurrent protection, and when we have to have secondary overcurrent protection and when we don't have to have secondary overcurrent protection. So most scenarios that we come across will have both primary and secondary overcurrent protection, meaning you are going to have one circuit breaker or a set of fuses for the primary set, and one circuit breaker or set of fuses for the secondary set before we hit our branch circuit breakers. Now, there are scenarios where you can have, if you have 6 or less circuit breakers grouped together, that can count as a single, as your single set of overcurrent protection on your secondary. Not throws of the hand is another thing I've heard said. No more than 6 throws of the hand. So it can be either one or the other. But we have some scenarios here where you might have primary only overcurrent protection. So in Article 450.3, we have this table, and this table is for determining the maximum rating or setting of overcurrent protection for transformers 1,000 volts or less. And these values are determined as a percentage of transformer rated current. Okay, so there are some scenarios where we have to have secondary overcurrent protection and some where we don't. The only scenarios where we are allowed to consider the secondary to be protected by the primary overcurrent protection device, and this would basically mean that we have a circuit breaker that feeds the transformer, and then the secondary of that transformer is tied directly to the load, directly to the motor, directly to the relays, directly to whatever it is, right? There's no, between the secondary and the load, there's no overcurrent protection. So this is the scenario we're discussing, but we're only allowed to do that in a very limited capacity. And so I've highlighted that here. This is from Article 450. No, this is from Article 240. I can't remember. And it says we can have primary only overcurrent protection with single phase. Excuse me. We are not allowed to have primary overcurrent protection only when the system is single phase other than 2-wire and multi-phase other than delta 3-wire. Transformer secondary conductors are not considered to be protected by the primary overcurrent device. I think I get into more about that in some of the next slides. Now, we're not going to see this very frequently. Most of our scenarios are going to have this other condition where primary and secondary overcurrent protection is required. Because what are we normally installing? We're normally installing 3-phase transformers that have a center tapped neutral, right? And so that would be, I feel like I'm tripping up a little bit here. Okay, so here's an example of transformer that is allowed to have primary only overcurrent protection. Right, this is a transformer that's in one of our air current controllers. Right, and so we have 480 volts coming in, and we have a single voltage going out. We have 120 volts going out just as a single voltage. Right, and so that scenario is not one of these. So single phase other than 2-wire. Right, so the upper portion of this code, maybe I should read that, and that'll help clear this up. So we are allowed to have primary overcurrent protection only when conductors are supplied by the secondary side of a single phase transformer having 2-wire single voltage secondary, or a 3-phase delta connected transformer having a 3-wire single voltage secondary shall be permitted to be protected by overcurrent protection provided on the primary side of the transformer, provided that this protection is in accordance with 450.3. Okay, so the distinction here seems to be, is the secondary a single voltage system or is it a multi-voltage system? So we could just sort of maybe try to simplify this that way, where if it's a single voltage secondary, then sure, we can have primary only overcurrent protection. If it's multi-voltage, such as 120, 208, 277, 480, things, scenarios such as that, then we need both primary and secondary overcurrent protection. Right, and so this transformer here is an example of where we're allowed to have primary overcurrent protection only. And so let's do the math to figure out how to size our primary only overcurrent protection. And so if we go back to our table here, we can see that we have some scenarios here that say if currents are 9 amps or more, then our primary overcurrent protection has to be 125% of the transformer rated current. If it's less than 9 amps, then we're allowed 167%. If it's less than 2 amps, then we're allowed 300% as a percentage of the transformer rated current. And so this is a 500 VA volt amp transformer. So we can take 500 VA divided by 480. 480 volts is the incoming voltage. This will give us 1.04 amps on the primary. So that means that this transformer is capable of delivering a 1.04 amps on the primary. 1.04 times 3, or 300%, is 3.12. This means our primary overcurrent protection required for this device is 3 amps. And so I wish I took a photo of this while I was there, but more than likely, we would see that there is a fuse holder in this control cabinet that has a 3 amp fuse in it. That's what I would anticipate seeing here. So here's an example of a transformer required to have both primary and secondary overcurrent protection. All right, so this one has 480 volts on the primary, which on our primaries, we're always going to only have 1 voltage. We don't bring neutrals to transformers. So our primaries are always going to have one voltage. Our secondary on this transformer is 120, 240. So it's a multi-voltage secondary. Therefore, we have to have primary and secondary overcurrent protection. Okay, so our primary overcurrent, so let's do the math on this one. So for the primary, this was sort of interesting. I really didn't like this example because My primary and secondary overcurrent protection ended up like really close to each other, and I didn't expect that. But a primary overcurrent protection is at 15,000 volt amps divided by 480 gives us 31.25 amps. 31.25 times 250% gives us 78.125. So the primary overcurrent protection required is 70 amps. So we'll go back to this code article here, this table. We are more than 9 amps. Our primary overcurrent protection is allowed to be 250% of the transformer rated current. Okay. Then our secondary protection is required to be 125%, not more than 125%. It can be less. It can't be more. And so this brought these really close to each other because we're increasing this by 250%. This is what we're allowed to do. Now in our secondary overcurrent protection, 15,000 VA divided by 240 equals 62.5 amps. 62.5 times 1.25 or 125% equals 78.125. The secondary overcurrent protection required is 80 amps. How come I have 70 amps here and 80 amps here? The reason is because when we have a little note, there's a little fine print note here on our secondary protection here. Note 1 says where 125% of this current does not correspond to the standard rating of a fused or non-adjustable circuit breaker, a higher rating that does not exceed the next higher standard rating shall be permitted. So this is why on the secondary, I wrote we can have 80 amps, whereas we don't have that allowance on the primary. We don't have that allowance on the primary. That's why the primary side had to be 70 amps here. And normally we'll see a larger gap between these where the primary and the secondary aren't so close together. It's just this example that I picked being a 240 volt secondary versus like a 208 or something. It's just the way this math worked out. It put it pretty close. I think typically we might see something like 45 amps on the primary and then a higher overcurrent protection on the secondary. And there may be other reasons for that. Maybe the job was engineered just differently. Like these are max values, 250%. That's the maximum value you're allowed to put in the primary. You can be lower. In fact, you might want to be lower. Like maybe this is not how you would want to actually size this, because it's like, okay, if I have 70 amps, now I've got to run 4-gauge wire, but I really only need half of that for my capacity to feed this transformer. So I want to lower overcurrent protection. That way I can have smaller gauge wires and smaller conduit and all this. And these are some design considerations that you would take into account when you're putting something like this together. Okay, 650. So very briefly, tap conductors. So we typically want our transformers to be within 10 feet of the secondary overcurrent protection, your main breaker on your secondary or your fuse disconnect or whatever it is. Typically, you're going to want that to be 10 feet or less in distance. And that's because of this tap rule that, just to condense this all down, is that we have to be no longer than 10 feet. And that's basically just to give us a limitation on those unprotected conductors, because between that secondary termination of that transformer and your overcurrent device, really those conductors have no overcurrent protection on them. They're likely to be able to draw more load on them than the rating of those conductors, but there's really no way to resolve that. You have to connect point A to point B, and so we're just giving some limits on point A to point B, and then we're giving some rules as to how we size those conductors when they're less than 10 feet or less long. Let's see, for field and secondaries. And so the rating of these conductors, the secondary conductors, should not be less than the primary to secondary transformer voltage ratio times 1/10 the rating of the OCP device rating, blah, blah, blah. It's like, oh, it's so technical. If you need to size these conductors, you guys are almost never going to do this because this is all going to be engineered mostly. But if you are in a scenario, you're trying to figure out the size of your conductors and you're only 10 feet long. If you size those to your overcurrent protection, which is what you would probably do anyway, that's going to be fine. You don't really have to remember all of this voltage ratio nonsense to be able to know what size conductors. Just size it to the size of your overcurrent protection, which you've determined by by this math here. So 80 amps, I believe that to be 4-gauge wire. You're going to be fine with 4-gauge wire in a 10-foot tap rule and following a 10-foot tap rule. Now, there are some scenarios where 10 feet is too restrictive. You just need a little bit more. In fact, it's usually too restrictive. I think that most of our jobs out there are exceeding that 10-foot length just because structurally there's limitations that you just can't get that transformer close enough. And the engineer didn't design a way around it. And so we kind of get in this stuck scenario. Now, you can go 25 feet long, but what you then have to do is increase the size of those conductors. So if you're the rule with that is the secondary conductors must not have an ampacity less than the value of the primary to secondary voltage ratio times 1/3 of the rating of the overcurrent device protecting the primary of the transformer. So you have an out. There is a way out here. If you do have to be more than 10 feet long, you can make this adjustment and increase the size of your conductors accordingly. This is something that I'm pretty confident we've missed on several projects because we just follow the design. But this could be something, honestly, we could RFI this, right? And then the engineer is going to say one or two things. He'll say, okay, well, let's put a fuse disconnect within 10 feet. Well, I mean, that's going to result in a change order for us because it's a design change. It's not really our fault that we're being told to suspend a transformer and that feeds a transformer or a panel that's probably on average at least 15 feet away in terms of secondary conductor length. And so, hey, Mr. Engineer, like you didn't think this through thoroughly enough. This is the rule. 240.21c says blah, blah, blah rules. What do you want me to do about it? Oh, I want you to do this. Cool. Here's the extra expense for that. Because if our goal is to follow code, follow rules, to have a correct installation or as close to correct as we can get, we do want to make sure that we're covering these things. But is it going to burn down the building? Does it really introduce any electrocution risk or anything? No, because those conductors are going to be limited. There's no additional current that's going to be introduced onto those circuits. It's all still going to be limited by that breaker. I don't really understand why these tap rules are here other than just to prevent this scenario where somebody runs all the way across a building, right? So sometimes there's these rules in the code just that they don't really make a whole lot of sense if you think about, well, what's the risk? Until you start thinking about what is the dumb thing somebody's going to do if this rule doesn't exist. So you need a way to enforce it. And my sense is that this is where some of these tap rules come into play. Oh, and then last slide is service disconnected means. This is something I learned just the other day. Transformers other than class 2 or class 3 transformers shall have a disconnected means located either in sight of the transformer or in a remote location. Distinction, we're talking disconnected means. We're not talking overcurrent protection. You can have just a safety switch, right? Just no fuses or anything in there. So they shall have a disconnected means located either inside of the transformer or in a remote location, or just put a label on it. This is a bad photo for this distinction, or just put a label on it that says in detail where that disconnected means is. And so this is something also I think we're missing on a lot of our transformer installations is we aren't putting proper labeling on that transformer, because in almost all scenarios that we have in our stores, our primary is coming from the circuit breaker is in some remote location far away, and we are not installing a safety switch on that primary before it enters the transformer. And so if we're not going to install a safety switch there, because typically it's not designed that way, we have to make sure we're labeling these transformers properly in order to satisfy 450.14, which I don't think we're actually putting the distinction about, oh, here it is, shall be filled marked on the transformer. We're located in a remote location. The disconnected means shall be lockable in accordance to 110.25, and its location shall be filled marked on the transformer. So those are the two things to make sure to mention. One, we need to have a locking means on that remote breaker, and we need to have it properly marked on the transformer at the location of that breaker. I think those are two things we haven't been doing. So now that we know, we can start doing it. Okay, that's it. That's all I got.